In this lesson, we're going to examine the idea of a confidence interval. The whole time we've been talking about statistics and probability, we've been making these predictions, percentages, and saying, oh, this is the likelihood of something happening. Well, the challenge in statistics is you can't always be sure. Sure, theoretically things should happen, but practically, oftentimes, other things happen. So this is where the idea of a confidence interval comes into play. So let's pretend we're examining a sample, a group of people. Well, that group, it hopefully represents the population pretty well, but it's not always going to be perfect. However, if we can assume that the population is normally distributed, then we can determine an acceptable confidence interval, a range into which certain values falls. This range is calculated by finding the margin of error. Okay, so for example, let's say we have a poll, and it states that 80% of people are going to vote for a smoking ban. Well, the poll doesn't cover every single person. We've interviewed some people. So we can't say for sure that 80% of people are going to vote for this smoking ban, but we can develop an acceptable range. Okay? The way that's going to look is we're going to say something like these results are accurate to within plus or 4%, 19 times out of 20. So what does this all mean? Well, let's take this first of all, 19 times out of 20. Well, 19 out of 20 is 0.95. In other words, we can be 95% confident, 19 times out of 20, that between, I think we think 80%, but that's only accurate to plus or minus 4%. So if we subtract 4 from 80, we get 76. And if we add 4, we get 84. And then we can be 95% confident that between 76 to 84% of the population actually supports the ban. And we call this a confidence interval. So our job today is to try and establish these intervals. How confident can we be? What range are we willing to allow, say things could fall into? And how accurate is that going to be? Okay, so there's a couple of things you need to think about here. Okay? The margin of error, first of all, depends on a level of confidence. Do you want to be 95% confident, 99% confident? Well, you're willing to be 50% confident, probably not 50. And we do that by finding a z-score. Okay? We need to know a probability, the likelihood of something actually happening, 80% of people supporting it. We call it the letter P. P can also think about it stands for proportion. And we kind of need to know how many people we actually looked at, our sample size. We use a symbol N for that. Okay? If we only look at 2 people, that's not really a good sample. Our level of error is going to be really high. Our margin is going to be really wide. But if we had, I don't know, 2,000 people, odds are it's going to be a lot closer. The overall formula, E, our error, margin of error, okay, is found by Z times the square root of P times 1 minus P, all divided by N. Okay, now it looks complicated. It really isn't. We'll try a few in a second here. Okay. The common confidence intervals that we usually use are we want to be 90, 95, or 99% confidence. In other words, we're willing to allow 10% error, 5% error, 1% error. There are Z-scores, 1.645, 1.96, and 2.576. So these would be the Zs we use here. Okay, one of those 3. So let's take a look. In a 2012 survey, 142 people out of 200 were satisfied with their job. We tried it again the next year, and 160 people out of 220 were satisfied with their job. Can we figure out the percentage, the p-value, of people satisfied with their job for each year? Well, sure we can. We can do 2012. P will be 142 out of 200. Okay, just type that into your calculator, and you should get 71% or 0.71. Okay, in 2013, let's see what happened. Our p-value is now 160 out of 220. which gives us 0.7272, or it says in percent, so 71%, and 72.7%. Oh, so based on this, we could say, hey, you know what, people are more satisfied with their jobs, right? And it's gone up. But can we say that? Let's take a look. Let's find the margin of error for each year. We're going to use a 90% confidence level. This tells me my Z value. Okay? From our last screen, a Z value of 90% is 1.645. Okay, so let's give this a try. What's our margin of error? How accurate are these numbers really for the entire population, not just the sample? So our error equals, this is our formula, Z bracket, or sorry, root 1 minus P divided by N. So if we try 2012 first, our Z value we said was 1.645. Square root of P, we just figured out was 0.71. 1 minus P, okay, like that. That's our Q value, if you will. And how many people were actually interviewed in that year? There were 200. That was our N, right? Number of people we talked to. Yeah. We're going to put this into our calculator. Okay. Hopefully figure out the number underneath the root sign first. So I would type all this in the way it looks. Or if you want to, you can use 0.29 for that. Figure out that number before you square root it and before you multiply by 1.645. If you do it right, hopefully you end up with 0.053, or if you will, 5.3%. We'll do the same thing for the next year in 2013. Our Z value is still the same. The only thing that's different is we have a different P, 0.727, 1 minus 0.727, divided by, and that year we interviewed 220 people. Some more people, slightly more accurate probably. Okay, what do we get for that one? I get 0.49, or if you will, oops, that's not right, 0.049, that's the number there. Or 4.9%. There's our margin of error. I want to figure out the confidence interval for each year. So where does the actual job satisfaction fall? So in 2012, we thought 71% of people liked it. But that was accurate to a margin of error of plus or minus 5.3%. So how many people actually like their job? Between, if I add it, 76.3%, and if I subtract it, 65.7%. If I go to the next year, we had 72.7 plus or minus 4.9. So again, if we add it, we've got 77.6% of people might have enjoyed their job. And if we subtract it, we get 67.8. And so we can be 90% sure, and I'm saying 90 because that's the Z score that we use in this question, that these are the ranges in each year of who actually enjoyed their job satisfaction. Hey, do they overlap? Well, if we take a look, yeah, the top numbers here are higher than the bottom numbers here. So yeah, they overlap. And the question we ask is, well, why is that important? Well, because we don't know the actual values. When I get to question E that asks me, can you confidently state that job satisfaction is increasing? No, I can't. Since there's that overlap, theoretically, in 2013, these numbers could be the accurate ones. Maybe only 67.8% of people like their jobs. And in 2012, maybe these people are the people who like their jobs. So despite the fact that my p-values in the beginning of the question were going up from 71 to 72.7, the confidence I have in those numbers is such that I don't know what actually happened. Okay? We cannot make a conclusion that satisfaction is increasing. If there was no overlap, then we could. If the numbers in 2013 were definitely higher than numbers in 2012 on both ends of the spectrum, then I can conclude that. But because there's an overlap, I don't know what's actually happening here. Okay. Let's see if you guys can try part of one, not the whole thing, just part. A study of 4,000 recent graduates found that 64% of university graduates found a job in their field within the first 3 years. Determine the margin of error at 95%. Okay, so our error. A z-score of 95% comes off that table. It's the number 1.96. And our p-value. What proportion of people actually found this? Oh, it's 64. All right, our q value, 1 minus. And how many people do we interview? 4,000. So our margin of error in this case is 0.015, or in other words, 1.5%. So for what range of percent could you be 95% confident that a university graduate will find a job? I could be 95% confident, just to move that down a little bit, that 64% have found it of our sample, but that's accurate to plus or minus 1.5%. So in other words, probably 95% sure that between 62.5% and 65.5% of people actually find a job within the first 3 years, based on the size of my sample and based on how confident I want to be. Now, the nice thing about this formula is we can actually work backwards. We can figure some things out about surveys. So if we look at this next example here, we have a recent survey that 82% of students graduate within 5 years of entering grade 9. This result is considered accurate within plus or minus 3%, 19 times out of 20. Estimate the sample size. So what I can do with this is I can actually work backwards and say, well, how many people did they interview? Was it a really small sample and that's not a very good survey, or was it a reasonable size and it should be fairly accurate? And I can do it by manipulating this formula here. Okay. We're not changing the formula, we're just going to manipulate it a little bit to work and solve for the n. So what do I know? Do I know the error? Well, yeah, it says plus or minus 3%. And now when we do this, we're going to turn that 3% into the decimal, because that's usually how we work with these things. The z-score I know, because it says 19 times out of 20, which I know that 19 times out of 20 is 95%, or a z-score of 1.96. I know my p-value is 0.82, so 1 minus p is 0.82. What I'm really trying to figure out this time is n. So here's how we can manipulate this. The first thing I want to do is I want to divide out the 1.96. Okay. And I'm going to fix the number inside the bracket to make it easier to work with. Okay, so I brought this over here and divided, and I figured out what happened here. The next thing I want to do is I want to get rid of that square root sign. And I can get rid of square root signs by doing the opposites. In other words, if I take this number and I square it, I'll get rid of that square root sign. Okay, so now I have no root sign to worry about. Now, I can do this math. I get a big nasty looking decimal here. That's okay, not a big deal. I get 0.00, one more zero there, sorry. 3 zeros. 2, 3, 4, 2, 7. It keeps on going. On the right-hand side, if I multiply those two things, you get 0.1476 over n. Well, to solve this, I have to cross multiply. In other words, I get 0.000234427n equals 0.1476. And n is going to be 1476 divided by the big, long decimal. 23427. Which gives us an answer of 630. Okay, now, that's not super hard to do that. Okay? It's the same process every time. But sometimes, it might be easier to just think about rearranging the formula rather than having to rearrange the numbers. So if you think about it, okay, this is my error, and this is my z-score. And when I go to this row, I go to error and z-score, but I want to square it. Okay? This number here is p times q, if you will. Right? This is p, this is q. And if I take that to the very end here, I already have p times q divided by the error over z squared. And that will always give you n. So if you like the idea of rearranging a formula rather than rearranging numbers, here's our formula. Here's our rearrangement of what we got. Oh, I'll attach those together here. How about that? Okay. So if you want to solve for n, here's a handy formula for doing it. You just have to be comfortable with working the formulas. Now, that's two ideas. There's three we're going to look at today. The third idea is sometimes we want to examine a sample rather than a population. And we know it's kind of way easier to do, right? We can look at a small group of people rather than the entire people. And we can talk about proportions like we've been doing, percents, probabilities. We can also look at means, what happens on average. Because what happens on average to a sample has some effect on what happens on average to the population. And the way we do this is by doing repeated samples of that population. So we want to talk about grade 12s at our school. We would take a sample of them. We're going to take 20 of these grade 12s, and then we'd do the next group of 20, 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 and we would average those. Okay? So the mean of our sample gives a pretty good estimate of the mean of the population. But the trick is the standard deviation is going to change because you have so much variation from class to class to class. So if I want to give a sample standard deviation, we use this symbol, sigma x. What we have to do is take the sample, the overall standard deviation, and divide it by the root of our sample size. Okay. These predictions that we're going to get are going to be better the bigger this n value is. The bigger your sample size, the better your predictions, which makes sense. And the reason why that works is the bigger the sample size, the smaller root n becomes, the more accurate, the better that it reflects the standard deviation of the overall population. Okay. Once we do that, we can then figure out a confidence interval for our mean. And a confidence interval is given by the sample mean plus or minus your z-score, same old z-score, times the standard deviation of x. And as a general rule, we always say we want at least a sample size of 30 to produce a reasonable estimate. Anything less than 30 is not statistically relevant or accurate. Bigger than 30 is better. Yeah, so let's give you an example of how this is going to work. So we have basketball players. The heights of them are normally distributed. Coaches are going to make a balanced team. He obtained the following sample of players' heights. So he went out and gathered some data. From past experience, he found that heights are normally distributed with a mean of 170 and a standard deviation of 9. Can we find the sample mean and sample standard deviation of these data? So our sample mean. I want to find the mean of these things that we have. Well, that's a good old graphing calculator question, right? Let's turn it on, clear our memory. Oops, a second. Plus 7, 1, 2. All right, we're going to put our data in. Stat, edit. Haven't done this in a long time. We got to put all these data in here. So we got 186. We have 165, 158, 176, 181, 178, 154, 166, and oh, I got two more, 163 and 168. Okay, stat, calc, 1-bar stats. This is good practice getting us ready for exam stuff. And the average for these basketball players turns out to be 159.5. That's the sample mean. Based on this sample, I can probably predict the population pretty well. Okay. My standard deviation of this sample is 33.56. But our sample is pretty small, so we have to divide that out by the size of the sample. There are 10 pieces of data. I can go and count the less or look at my graphing calculator and it says the number 10. Actually, that number seems pretty high. Let me look at my data again here. I think I may actually have a typo there. Stat, edit. What do we got here? 186, 165, 158, 76, 81, 78, 9, 54, 166. Oh, look at that. Put a 163 in there. Let's try this again. That's better. Stat, edit. It seemed really high for standard deviation. That's how I kind of guessed that. Okay, there we go. Much better numbers. 169.5. And a standard deviation of 9.84. Okay, so if I want to calculate this, I got to take my 9.84 and divide it by the root of 10. That's the size of my sample. Okay, it's going to make my standard deviation smaller. My standard deviation for my sample is actually going to be 3.11. Okay. Now I can take that to use it to make a confidence interval. Okay. I couldn't use such a big standard deviation as I started with the 9 because my sample was so small. I need to make my standard deviation smaller. Okay, so our confidence interval, where does the mean actually fall for the population? Well, we can probably be somewhat accurate based on our old mean, plus or minus our Z confidence, and our standard deviation. We found that the mean for our sample was 169.5. We were told that we want to be confident 90% of the time, which is the number 1.645, and our standard deviation is 3.11, based on the size of the sample that we actually took. It's not the standard deviation of the sample, it's a better estimate. So where does our mean actually fall? Well, if we take the 169 and we do the adding part, we get a height of 174. Or if we do the subtracting version, we can say 170.97. We can be 90% confident it's actually between those two numbers. That's a more reasonable estimate. Okay, so that's the end of confidence intervals. Lots of things that are basically working with formulas, an idea of that. Some questions to try and get comfortable with those formulas. It's really more about, we know we're not accurate, and that's part of the problem with statistics, but how accurate are we? How confident can we be in these answers?